Hey everybody, it's Ripley back again. Oh, today's the extension into 3-space of maxes and mins. This is kind of a famous little diagram right here to sort of show you what maxes and mins and saddle points, as importantly, saddle points look like in 3-space. So, as you would expect, remember when we were in 2-space, we know what maxes and mins, abs, maxes, I showed this to you guys a bunch, like this, something like that. This is an abs max, relative min, relative max, absolute min, relative max. Same sort of thing, except now think about this. Remember how we defined, if this is f of x, if we defined this guy, let's say this relative min or local, or excuse me, relative max or local max, how did we define that as local max or relative max? We said that there exists an open ball, which in the one-dimensional space on x-axis, so here's if we have a max at, say, x equals a, there was an open ball around x equals a. Now, remember we were like, open ball, what? It's a line, that's an open interval. Yeah, but you're about to see why that becomes a little bit more intuitive, or more important, as it were. If I can open up an open interval around x equals a such that f is greater than or equal to all of the values when those values are sent onto the function, then we have what's referred to as a local max. If it's greater than or equal to all of the values, if it's a local max, but it's also a max that's greater than or equal to all the values on the entire interval, then you have an absolute max, right? So what we're going to do is we're going to define that in 3-space. But before we do that, let's identify a couple things. Should be relatively easy to see that this is an absolute. Do I have that on black? I do. That this guy right here is an absolute min. This guy right here is an absolute max. And then notice that these guys are in different parts of the curve, aren't they? Different x values. Totally different y values, even different z values, where I get this local max and this local min. This local min appears to be in the negative values. Now, what of x, excuse me, not of, well, I guess it would be of z as well. What is this? Well, what's it look like, especially in 3-space? This guy right here is the saddle point. And that's going to have some very interesting characteristics, because you could say, wait a sec, Ripley, if I follow this contour line up and over, right, of this space, that kind of appears to be a max. But wait, there's more. If I follow this, whoa, what did I do now? If I follow this guy, then it appears to be a min. Yeah, exactly. Saddle points behave as maxes and mins in different planes. And that's why they're saddle points. That's why they make that saddle. Now think about what a local max, an absolute max, a local min, or an absolute min. Remember, we use these as relative and global too, so don't be afraid of the terminology. Then in any plane, if I were to cut through that point with any plane, it would look like a max in that plane, period, every time. Does that make sense? If I use those level curves, remember level curves, but I think of it not as on the xy plane, but as I think of it as cutting with some sort of vertical plane that's parallel to the z, excuse me, then I've got myself a max, no matter what I do, all right? It's kind of an interesting way to look at it. Okay, so let's get some formal definitions out of the way. Per the book, all right, we say f of xy has local or relative, local slash, you can put me on fast speed right here, max at a comma b, if and only if f of x y is less than or equal to f of a b for some values, or let's say for some open circle around. Now remember, this circle could be referred to as a ball as well, right? It's just in 2-space now. I'll show you what I mean by that. For some open circle around AB in the XY plane. All right, actually, listen, I'm running like that. That's terrible. You said, Ripley, what are you talking about? in R2. So I think I drew this awful thing for you guys before. All right, so let's keep it super simple. Clearly, I'm going to have a max. When in doubt, go back to my little hemisphere thingy-dingy, right? And this is the outside of the hemisphere. Here's going to be my abs max. And then down here, remember how we defined D as being the domain? That guy's going to look like this. All right, now there is a point which we are calling AB, which is our max. When I project that up, this is F of AB, right? That makes sense? Now, if it's a relative max, that means that I can draw an open circle, just like I could draw an open interval, around AB that's centered at AB, such that F of AB is greater than or equal to all of the values in that circle. All right? That makes sense? It gets a little crazy, all right? When you're trying to, when you do it in 3 space, you've definitely got to rearrange your brain a bit. All right, so if I want a relative min, I'm not going to bore you with this. It should be relatively easy. Sorry. Make less than or equal to's into greater than or equal to's, and we're in exactly the same boat. Okay? Now, unless it's a trite example like this, or let me see, let's go back to this guy. Like, we know, when I look at this, hopefully you can look at this thing and say, okay, z equals x squared plus y squared. You should be able to sort of sketch this figure out relatively easy, right? It's like an egg shape, because if I set y equals 0, then I get z equals x squared, which is parabolic, moving up the z-axis. If I set let's see, if I set x equal to 0, then I get z equals y squared, and I end up with this parabola. It's relatively easy to see that I'm going to have a minimum right here. It doesn't take a whole lot of hand waving to be like, well, clearly, duh, it's a minimum because I have these parabolic things that happen when x equals 0 and y equals 0. Now, this can be a little bit confusing. You see how this says z min? Well, z min in this case is at 0. They set it at 0. I think it says somewhere over here. Yeah, it sets it auto. So watch, if I change this to 0, and then I go up to, I don't know, 4. Watch what happens. Bam. I get the same thing. There's no difference. All right? I've reset the thing. Did I reset it? Oh, I didn't want to do that. Let's go back. Bam. Oh, what the heck? Anyway, before I'm a wingnut, this is automatically setting this point right here at 0, 0. Actually, 0, 0, 0 in 3 space. So ignore the guy who's acting like a yahoo. Now, what I'm going to do is I'm going to give you a way to solve these things. But first, I have to give you a theorem first. Last page was a definition. This page is a theorem. All right, so we got ourselves a theorem because we're going to use, partial derivatives. They're not just for fun anymore. Now we got to use them. We got to put them to work for us. All right, so the theorem is this: if f has a local max slash min at point AB and first order partials, I'm kind of lazy with the dash, the partial, sorry. The textbook uses the dashes. I'm kind of lazy with that. Partial, I'm going to just call them partials again, of f exist at AB, at AB, this implies that the partial with respect to x at AB equals the partial with respect to y at AB equals 0, which kind of makes sense, right? I mean, that says that the change, remember how the partials work, right? The change along the x if I fix y, and the change along the y when I fix x, if I go back here to this max, like if I fix y at b, so if this point right here is a comma b, and I fix b, then the derivative along the x had better be 0. Likewise, if I fix x equal a, then the derivative along the y, along that plane, had better be 0 as well. Kind of makes sense, because what it's basically doing is it's creating an image on a plane. So this can sort of be distilled down to, okay, if I've got if I'm going to have a local max or a min, then the planes that contain the curves are going to make, if I've got this plane, then they're either going to make a max, right, or they're going to make a min. Now, both of these both the planes that are created by the partial derivative with respect to x and the partial with respect to y are going to look like this if it's going to be a max, and they're going to look like this if it's going to be a min. Okay, now, deep breath. I need to show you how to do this analytically rather than just being able to look at a graph. Okay, it's called the second derivative test. All right, so we're going to do the second derivative test. And as you've probably seen with partials, when you start talking about second derivatives, all hell can break loose pretty quickly. All right, so let's talk about what the second derivative test really says. And I'm going to give you the full panoply of information, excuse me, that is given in the second derivative test for three-space functions. All right, so you ready? Here it goes. It says, suppose second order partials, oops, not partials. That would be really funny if they were called partials, because you know what you would, never mind. Anyway, second order partials of f are continuous, which means I can take them, right? Are continuous. They exist on a disk, just like what we talked about before, centered at AB, and the partial with respect to x at AB equals 0 equals the partial with respect to y at AB. Okay? In other words, what would we call this if both the partials were equal to 0? Well, what do we call it when a derivative was equal to 0 in two space? What does that say about f of AB? Well, it's a critical point, right? When first derivatives equal 0 or do not exist. Now, we're not going to get into that quite yet. Now, you ready? Here it goes. And this is going to be the most unintuitive thing that you've probably seen in this class. You're just going to have to swallow it. It's a drag because I can't prove it to you per se. We just don't have the mathematical vocabulary to do it, okay? I'm going to let this D. Now, this can get a little bit confusing, all right? Because we have defined D before as being domain. Remember, this guy was referred to as D. So our notation, as our esteemed author is apt to do, sometimes gets a little muddled. I apologize for that, but we're sort of stuck with it. We're going to let D be D of AB, and he should have called it just B or whatever. Now, you ready? Here we go. This is the partial with respect to x, but it's the second partial. So remember, I take the partial with respect to x, and then I take another partial with respect to x, and that guy's at AB. And then I'm going to multiply that times the partial with respect to y, but it's the second derivative. So let's just call it the second partial. I'm being overly onerous here. All right, and then I'm going to subtract. Now here's where it gets fun. This is the partial, it's the second partial, but it's fxy, which means I take the partial with respect to x first, then I take this partial with respect to y next, and then I do AB, and then I square this. Okay? Think of this not as D as in domain, but think of it like, remember b squared minus 4ac in the quadratic? It's the discriminant. All right? It discriminates. But it's not truly a discriminant, so because I don't want to confuse that with an actual discriminant when we use the quadratic, okay? It discriminates what kind of optimization we have, whether it's a max, a min, nothing, which could be construed as a saddle point. Okay, so you ready? Here we go. A, if D is greater than 0, and the partial xx at AB equals 0. This implies that f of AB is a min. All right? Be nice. Be nice to yourself. You're just going to have to eat it. And I'll probably let you use some notes on this, but maybe not. I don't know. You should probably know this because it's a biggie. Optimization is huge. If D is greater than 0, you can probably predict what this is going to be. And the second partial of x is equal to, I'm sorry, is, whoa. I lied on these. Let's not get too hoopty here. Sorry. If D is greater than 0 and the second partial is greater than 0, see, it's easy for me to make a mistake. Then I have myself a min. It's kind of like this guy right here is the concave up that we used to use. Remember, if the second derivative, if f primed at a equals 0 and f double primed at a is greater than 0, this implies concave up. So I have a leveling off, which produces that min. Likewise, okay, here we go. If d is greater than 0 and the second partial with respect to x is less than 0, well, that's like saying f double prime at a is less than 0, therefore concave down, and I get this guy. This implies f at ab is a max. Okay, how about c? If d is less than 0, this implies that f of ab is neither, which implies what? I probably shouldn't have done this. Let's erase this really quickly. What does that imply for part C? If I have a critical value, but I have neither a max nor a min, if I just extend my understanding of 2-space, wouldn't that imply that f of AB is a saddle point? All right? So it's pretty useful. It's kind of helpful. Kind of works the same way, but it's got this ugly notation. And you may say, well, Ripley, why are we taking the second partials only with respect to x and not y and not xy and not yx? Shh, hush. Now, the textbook gives you a nice little, oh, whoa. Wait, whoa. We've got one little thing we got to deal with here. What happens if, let's do this as, I don't know, I'll throw d in here. What happens if d equals 0? No good. I have no information. I have to do something else. All right, graph, use numerical analyses, etc. All right, you're basically stuck. But if we're dealing with real valued functions of a real variable, right, of in this case a real triplet, right, we're sticking ordered triplets in, then, or I guess, excuse me, of ordered pairs, so of a real ordered pair, then this definitely shouldn't happen if this is true. If this is true, excuse me, if these guys are both equal to 0. Okay? Or it's going to be painfully obvious what's going on. All right. The textbook actually uses something kind of interesting, and I think this is where they got D. So they're saying that D is actually equal to the discriminant of fx, x, fxy, and then fyx, and fyy. If you remember back from your matrix algebra, well, what would you get? Now, remember, we know that fxy and fyx, those can be interchanged. So what ends up happening is if I take the discriminant of this, remember that's the product of those two minus the product of those two. I forget what the name of the guy is that said that these partials could be flip-flopped around. It's a French name. I'll remember it at some point. It doesn't matter. I end up with this y minus f of xy, and then this guy is squared. Now, it's just a mnemonic device for remembering what D is exactly. It's a determinant. This, in matrix parlance, is a determinant. But I kind of like to determinant. I kind of like to think of it in terms of a discriminant, because it discriminates the type of optimization that you have. Okay? I'm having a hard time with my word finding skills. All right. Outstanding. Let's move on. All right, now let's talk about the extreme value theorem for a three-dimensional function. But let's revisit it in 2 dimensions. Remember, suppose f is continuous on a closed interval from a to b. We know f, actually this is continuous, well, it doesn't even have to be, excuse me, continuously differentiable. We know f has abs max and abs min on AB. All right, it's the extreme value theorem. We have extreme values anytime we have a continuous function in two space. However, remember, sometimes we had to check endpoints. So if you're already thinking about, wow, how am I going to be able to extrapolate this and address this in three space? Well, it gets a little bit tricky, and we got to be really careful. Now, to be able to do that, we need a little vocabulary first. One is called a closed set. This is some set theoretical stuff. If I've got a closed set, all right, so let's just look at this on the xy plane. If I've got a closed set, it means the boundary of that set is literally closed. It's not dotted, right? So it's the set of x, y, right? This would be defined as, so I'm going to call this B. B is the set of x, y such that, wow, that's ridiculous. Okay, it means that, so if it's closed, it means there's not going to be, it's not dotted, right? It's not partially dotted. There's not like an open dot here. Right? All of this in here is surrounded by a hard less than or equal to boundary line. Okay, that's the definition of a closed set. Now, bounded means, if I do a bounded set, that simply means I can draw a circle around the set. So even if I don't have a closed set in the Cartesian plane, so let's say I've got this guy, this would be bounded, right? Because I can draw a circle around it. That's all that it means, at its absolute simplest. I can draw a disk that contains every single point in that set, even though in the way that this is drawn, this is just a less than, right? That's easy enough. Okay, now, once we have that, wait, let's make sure we understand something. If I have a closed set, does that automatically imply that it's bounded? Well, yeah, that's pretty close, right? Because if I'm closed out, I got to be careful with these definitions, though. I want you to think about that. We can talk about that a little bit further. If I have a bounded set, clearly it doesn't imply closed. So which direction does, I know that this guy seems to imply this guy, and this guy definitely does not necessarily imply that guy, because per my example. But that does, I'm getting caught up in some semantics on this. What I would like to do is give you the extreme value theorem. So I'm going to give you the EVT for f of xy, which I haven't done this in a while. Let's call it z. Okay? So it is, suppose f is continuous on a closed, bounded set D. Now this D, as opposed to the determinant, is the actual domain of the function. All right, D, which is in R2. So what they're telling us is, suppose that our domain is closed and bounded. All right, this implies that f attains both an abs max, and abs min. Now, I'm going to put these, I'm going to write these as f of x1. This is what your textbook does. And f of, wait a second, f of x1, x2. What are you doing, Ripley? F of x1, y1. So for some value, y1 and f of x2, y2, respectively. In other words, there exists a point, right, such that I have a max, and there will exist at least one point such that I have a min in both cases. I could have a bunch of points. Just remember, visualize y equals sine of x. We had a countably infinite number of maxes and a countably infinite number of mins. Same sort of thing in this case. So, respectively, at x1 and x2, or y, I did it again, x1, y1, and x2, y2 in the domain. All right? It's basically saying the exact same thing as the extreme value theorem for Cartesian functions. The difference is I got to have this closed and I got to have it bounded. Before we had a closed set, but now we have to bound this thing in. We got to make sure that it's closed, all right, and bounded. In other words, I can't have it wander off on me into infinity somewhere. And I got to make sure that I pick up all of the domain. That's what that bounded part is. So in other words, let's say that I've got, here's my x, here's my y, here's my z, here's my buddy, right? And I got this guy and my old friend, and I know, let's put D down here in blue. Right, here's D down here. This is D. See, the problem is if I accidentally chop off part of D, there's no guarantee that this part that's chopped is necessarily going to give me a max or a min. All right. However, if I make sure, especially if this is dotted, right, I don't want that. So what I do is I guarantee that the entire D in this case is in there and that it's contained. So I don't have D like squishing out over here somewhere where I might actually have an absolute max or an absolute min that I may have missed. Okay? All right, now I'm going to explain, it's a really beefy, meaty way to describe the extreme value theorem in 3-space. But I'm going to give you the technique on the next page for figuring out how that's done. I'm not going to give you a lot of examples, as you've probably noticed in this class. Most of the examples we're going to do in class with the time that we have, because I don't want this to be example heavy, as it were. All right, so, but as always, you can look through the examples in the section. All right, you ready? So here's the method to find the absolute maxes and the absolute min. So finding abs max and min for closed bounded F, or excuse me, for closed bounded D. Let's rewrite that. That's a terrible way to write that. For F, let's put our F in here, on a closed bounded set D. All right, so same as always. Look, when I was back here, if you look at this, it appears that the way in which this thing is drawn, it appears that this, I mean, we don't really know what's going on out at the edge, but just like in Calc 1, Calc 2, we knew that we could find maxes and mins. They could be interior points, right? The domain of this is going to be floating here on the xy plane, right? And I can have absolute maxes and absolute mins that don't necessarily occur at the boundary line. But in this case, in general, what we're going to say is, step 1, find critical points. Critical. Now remember, guys, points in D. Remember how I used to gripe and moan about critical points versus critical values? Can you see why they're actually called critical points instead of critical values of X? It's more general if we talk about it in 3-space than if we deal with a very specialized case of the Cartesian plane, right? And then part 2. Now here's the hard part, and we'll go over this in class. Find the extreme values of the boundary. Now that's the hard part. Values, I'm writing very poorly, of the boundary of D. So we have to deal boundary of D. So we have to deal, man, my writing is awful, with that boundary edge, and that can get really, really tricky. So, and in some cases it's not feasible. You would have to have a calculator figure it out. All right. So think of this step as I'm going to change the color. Think of this step as, remember how we always said on a closed interval in Calc 1 and Calc 2 as check, quote unquote, endpoints. We're not checking endpoints, we're checking the boundary. But that's what I want your mindset to be. And then we have to use algebraic tools to be able to do so. And then whichever wins, so if I go compare values of f from parts 1 and 2, and then determine maxes and mins. And I should probably say absolute maxes and mins. And that's it. Now, in class, we'll go over how to check the extreme values of the boundary. All right? I just want to give you the notes. I want to get you there. And then we're just going to do a whole bunch of mathematics in class. All right? All right, you guys, that's the end of this section. Good times. I'll see you in class tomorrow, and we're going to we spend a couple of days on this, so we got plenty of time. Okay? Have a good day.